Hey everyone, welcome to our weekly live session. My name's Neil Kanungo. I'm joined here with Ryan Stigler. Ryan, you want to say hi to everyone?
Hey everybody, I'm Ryan.
Hey Ryan, good to have you on today. I'm really excited for today's session. We're going to be talking about retrieval augmented generation with LangChain. So, retrieval augmented generation, also known as RAG, has been a really popular topic with LLMs and vector databases. It's a way that you can extend the knowledge base of your LLM to your private data. You're able to search your data and query your data, create a chat GPT like experience with your data, and be very conversational with it, utilizing an LLM and utilizing a vector database for the knowledge base and LangChain as the orchestrator. So Ryan's going to be presenting on that today. And just a quick intro, I wanted to let everyone know that we are going to go through a sample notebook today, Python notebook, and you're welcome to follow along with that. You can find that on our Learning Hub. I'll show you how to get to that in a second. But first, make sure you're signed up for KDB.AI. You can go to KDB.AI in your browser and you go to sign up. You'll get a sign up page. Put your information in a simple form. You'll get a verification email. Click the link, and then it'll send you another email with your login information, a link to the KDBI cloud. And there you go. You'll be presented with KDBI cloud user interface where you can add API keys, manage your API keys. You can you can delete those if you need to and add new ones. I always recommend copying your API key just so you have it in case you lose it. And if you do lose it, just generate a new one. But that's how you sign up. And today I'm going to skip the vector database introduction. I've done that introduction for the past few sessions, and hoping that folks have gotten a good sense of how vector databases work. If not, you can visit our Learning Hub on KDB.AI or watch one of our previous sessions. But today we're going to talk about retrieval augmented generation. So in our Learning Hub on the KDB.AI website, you go to LangChain and RAG under samples. You'll see this page and you can click the link download from GitHub. And when you download from GitHub, you'll get a notebook. It'll take you to our GitHub where you can download a Python notebook, which Ryan's going to go through today. So with that, we're going to hand it over to Ryan. And one thing I did want to mention before handing it over to Ryan is that retrieval augmented generation is a is an evolving space. There's different approaches to it, and today we're just going to do a very basic use case with just simple retrieval augmented generation, or simple RAG, also known as naive RAG. This is meant as an introduction to get you introduced to the concepts of RAG, but we will have a follow-up session in a couple weeks where we're going to talk about different approaches to RAG, and Ryan's going to give you a quick overview of that. So Ryan, if you want to go into presenter mode, and I will add you to the stage. There
All
you go.
right, all good?
Yep.
All right, well, thanks everyone for joining. Again, my name is Ryan Sigler, and we're going to do a quick introduction into retrieval augmented generation, talk a little bit about what it is and how it does what it does. Then we'll do a look at like the high-level architecture of naive RAG, what Neil just mentioned. I'll briefly touch on some of the other RAG approaches, and like you said, those are things we're going to be jumping into down the line a little bit. But after that, we'll go ahead and walk through some code. So with that, let's get started. So retrieval augmented generation, what is it? And what does it do? So really, it empowers us to use large language models to answer questions about data that it wasn't previously exposed to. So if we use like ChatGPT, for example, it's not going to be able to answer questions on our own enterprise data or our private documentation, or even recently released like news articles or technical articles, because it hasn't been trained on these things. So how can we allow it to answer questions about this data that it hasn't seen. And really, at the core of it, that's what RAG does. It's a pipeline, an architecture that allows us to introduce data to the LLM and have the LLM answer questions about that data for us. So when we look at how we would set up the RAG approach, there's really two steps in this. And the first one is retrieval. And what that means is we are extracting the relevant data that we want the LLM to answer questions about. So our private data, recent news articles, whatever it may be, whatever we want to create an application to answer questions about, we would retrieve those relevant documents, those relevant chunks of data, and then feed that into the second step, which is the generation step. So that's where we take that relevant data that we found, that we've retrieved, and we present that to a large language model. And then the large language model is able to generate a response based on that data. So this is how we can answer questions about data that it hasn't been trained on. So today, the code that we're going to be walking through is a representation of naive RAG. And this is a high-level architecture of what that is. But I think to get started, let's just walk through this, and it'll give us a bit better of understanding about how this actually works. So we have a example data set, whatever it may be. I'm just using PDFs here as an example, but you can really use any file format. There's all sorts of file ingesters that will go through different file types. So whatever format your data is in, you can adjust that into this RAG pipeline. And when we're setting this up, we are using a large language model of choice. But one thing we need to keep in mind, with any of these large language models, is that there is a limited context window. And what that means is that we can introduce only a certain number of tokens, or in other words, a certain amount of information to a large language model at once. There's a limit on that. So it doesn't make sense in most circumstances to introduce our entire data set to the large language model and ask questions about that all at once. It makes more sense to solve that problem by chunking up our data into smaller pieces. So after we ingest our data, we will chunk it up. And we are going to do a full article on chunking, and there's a bunch of different methodologies that we can use to effectively chunk. So look forward to that, and that'll be coming soon. But after we have our data chunked up, the next step is we need to embed that data. And all that means is that we're taking our raw text and we're formatting it into a machine-readable language. So we're taking raw text and representing that text as numbers, and then storing those numbers in a vector. So what that represents is the raw text, but it also has an additional capability, which is it represents the words themselves. However, it also captures some context, and that means how each word relates to one another within that chunk. So there's an extra contextual dimension that we capture when we do this embedding. But after we have embedded all of our chunks, we then can store that into a vector database or a vector store. So KDB.AI is a great vector store to use. So when we get to this point, all of our data is now stored in vector embedded format within this vector store. And this gives us some really unique capabilities when we are trying to retrieve the relevant data that we want. So we have a user. The user wants to ask a question about this data. So the user sends a prompt or a query. That query is embedded the same way that these chunks are embedded. And then, so it's a vector embedding. And then we can do a similarity search between our vector database, which has all of our documentation and data, and that user prompt. And there's several different methods we can use here: cosine similarity, Euclidean distance, dot product, different ways to compare how similar these vectors are to each other. And after the similarity search, we will actually extract the most similar vectors, or in other words, the most relevant chunks of data from our initial data set. So now we can introduce this relevant data to our large language model, as well as the user prompt to the large language model. And this gives the capability for it to answer questions about data that it hasn't been trained on. It's answering questions about that relevant and contextual data. So then it can feed that response to the user. So this is the naive RAG pipeline, but there's some problems with this. And some of the other methods, more advanced methods of RAG, start to answer to some of these problems. But if we just look at this, what we see is that every time a user prompts, it's going to go to a similarity search here. But what if the user's prompting on something that's not even related to our data set? It's not really related to anything stored in the data store. Well, that means, or in the vector store. So that means it's likely that any relevant information we get really isn't going to be that relevant. So that could actually throw off our large language model. So we just need to keep that in mind when we're using the naive approach. And this is, this wouldn't be something you would likely want to use in production at all. This is maybe trying to get your head wrapped around this concept, doing some quick POCs to understand what retrieval augmented generation is and start to understand how to work with some of these tools like LangChain, for example. But there's some other methods, and I'm just going to briefly touch on these, and then we'll get into some code. But like I said, some of the failures with the naive method is that it's always going to go and do that similarity search. So a method like using an agent on top of your large language model, which is just really a wrapper around your large language model, which specializes in deciding next steps in your pipeline based on a user prompt. You can use that. So it wouldn't always go right into that RAG process. The agent could decide, no, let's just send this query directly to a large language model, or no, we can introduce a tool to an agent. So, we get a mathematics question in from a user, we can just send that to the calculator tool and get a response from that. So it gives a bit of reasoning to how the bot is going to react to a user prompt. It's a bit of a heavy process, though, because to do that reasoning, we do an initial call to the large language model, which decides those next steps. So just be wary of that. Another method we could do is called guardrails, and this is a package that was released from NVIDIA NeMo. But it's an interesting method that combines like a traditional chatbot design method where you're explicitly writing out that dialogue flow, along with these more advanced like RAG and large language model methods. But what it does is it gives you the opportunity to actually define certain topics and then give specified responses to those topics. So if we didn't want our bot to answer questions about politics, for example, we could have a preset response built right in, or in other words, as a guardrail for our bot. So it's not going to send a political question to the large language model, it'll just send a preset response. So it allows us to be a little bit more safe with how we're setting up our chatbot or digital assistant there. And then another final method is using knowledge graphs. So knowledge graphs are a growing in popularity type of a database that instead of representing data in columns and rows, it represents as nodes and edges. So it's a graph, and it's really good at representing data that's, I would say, highly dependent on relationships. But when you have a knowledge graph, you can really do RAG on it in a similar way that you would do with any other type of data. And that is just instead of chunking up your data, you would just be taking specific nodes and embedding those nodes that have a certain amount of data associated with them. You do your similarity search and you pull out all the relevant nodes of data that are in your knowledge graph. But where you get a bit of additional capability is because you get these relevant nodes back that are in your knowledge graph, you can actually do some extra traversals throughout your graph and find maybe nearest neighbors or surrounding nodes with their metadata and data as well. So you're able to pass relevant nodes to the large language model as well as extra surrounding context. So the more context you can provide, the better. So these are just three approaches. It's a really fast moving space, so I'm sure there's more out there and more to come, but we will be covering these at a later date. So With that,
Hey Ryan, we did have a question in the chat.
yeah.
So probably was asking, and I think you kind of just discussed this a little bit, but maybe just reiterate.
Mhm.
So the question was, given the LLMs are not rule based, how can you guarantee that it'll know to use the augmented info that you provide in order to produce the final response? How does the LLM know? And I think you talked about that with some of these different approaches, but if you want to highlight
Yeah,
a general approach again.
exactly. So in the naive approach, you're right, it doesn't know. And it just will go to the vector database and do a similarity search right away. And if you're not prompting about data that you've stored in here, then it's likely not going to give you very relevant data back. But with some of these methods, you actually introduce some reasoning capability or some guardrails capability to sort of steer next steps. So we don't always need to go uh, through that retrieval process if we're not being prompted on data that's related. So there is that capability. It's just not in the naive approach, but in these more advanced approaches, there's the capability to actually structure how we are going to move on through this pipeline, whether we go through the RAG process, or we could send a direct response to the user, or if we just have a more of a general question, we can just send it to the large language model and have the language model handle it by itself.
Yeah, and just to reiterate for the audience, in 2 weeks, not next week, but the week after, we're going to go over these RAG approaches. Ryan's going to join us again, and we'll go over these approaches as well as some other approaches as well that are not included on the slide, just so you get a sense of the different ways to optimize RAG in own your own applications. And the week after that, we will actually talk about performance optimization with RAG. So we have some good sessions upcoming. Just keep an eye out. Wednesdays at the same time that you're on today, we'll have those sessions for you. So anyway, sorry to interrupt, Ryan. Please go ahead.
Oh, no problem. Thanks for the question, Prabhu. So let's get into some code. All right, so we have a notebook. This is the notebook that is on the KDB.AI samples page, so feel free to follow along. But so let's go ahead and just get started. So the first thing we need to do is install some requirements. So I've already done this. It takes a couple minutes to do that, but you can go ahead and install those requirements. And then we need to import our different packages. So we need to import our KDB.AI client, and this will allow us to connect up to KDB.AI to our vector database. We have LangChain packages, and just a quick note on LangChain. So this is just an open source framework that allows us to work and build applications with large language models. There's a ton of capability in this. Highly recommend checking it out. But they offer all sorts of packages to help us build out this retrieval augmented generation pipeline. So we'll import these. And then after we do our imports, we just need to get our API keys set up. So we're going to be using an OpenAI API key here and then the Hugging Face. I've already done this, but when you sign up for accounts with both of these providers, you can get your own API key there. So let's get into it. So we need to load our documentation.
You're doing it with OpenAI and Hugging Face in parallel in this.
Exactly. Yeah. So when we get down into actually performing our RAG pipeline, we're going to do a bit of a comparison between the two. So we're going to use a large language model from OpenAI as well as one from Hugging Face and just see some of the differences there.
So you only need one, but we'll do a comparison with both. That's great.
Exactly. Yeah. Thank you. So yeah, when we get into this pipeline, so the first thing we need to do is just load our data. And we use text loader, which is something you get from LangChain. And they have all sorts of different types of loaders. So you could do, Excel, CSV, PDF, different things like that as well.
There's tons of loaders. I was looking at the LangChain
Yes.
repo and LangChain website, and there's lots of loaders in the documentation, from reading websites, reading like Wikipedia pages, reading JSON. So I mean, like it looked like there's like 100 of them. So there's tons of ways to load data into your vector database. Now, is this the retriever part, or does the retriever part come later?
So this is the beginning of the retriever part, because we need to get our documentation loaded before we can really do anything. So if we just take a quick peek back at this pipeline, this is this step right here. So we're just loading our data in. We haven't chunked it yet, but so we are loading our data, and then we need to define a chunker. So there's all sorts of different chunkers out there, but this is a chunker from LangChain called Recursive Character Text Splitter, and this allows us to define like what our chunk size will be. And we're going to be diving into how to decide the optimal chunk size in the article that will be published coming up here. But you can also create a chunk overlap with this package, which is pretty interesting because it allows you to like keep, if there's some ongoing context between chunks, it won't just cut it off. So you could, set a 20, 50 character chunk overlap if you wanted for each chunk.
And that's not characters, but tokens, right?
So in this case, it's actually characters.
Oh, because you're using a character.
Exactly. Yeah, it's characters, but there's other methods that are specific to tokens as well.
Okay, great.
So we have this defined now. We've got our chunker, and now we go ahead and we'll run that, and then we need to actually do our chunking. So this is just calling that text splitter on our documents that we just ingested. So this is where we do the chunking. So all of our stuff is chunked now, and we can take a quick peek at what the first chunk is. So we're doing the State of the Union here. So this is just like a small paragraph of a chunk that has several sentences in it. So at this point, we have our data.
And I sorry, I was just going to point out the State of the Union address. This was after this speech was after ChatGPT was trained. ChatGPT goes to September 2021, and this State of the Union's after. So as a proof point, when we go through this sample, we ask questions of it, you'll be able to see that it's in fact not using the sequence-to-sequence modeling of ChatGPT. It's actually using the vector database in LangChain.
Yeah, that's a great point. So the next piece of this is the embedding. So we got our chunks and raw text created, but we need to embed them and put them in the vector embedded format. And to do that, we use an embedding model. Now, there's several different models out there. There's many embedding models, like Hugging Face has several as well. But we're going to use OpenAI's embeddings. Text embedding added 002. It's a really popular embedding model. That's been used in many of the demos that I've viewed myself. But I know that this stuff is always being updated, and there's likely going to be even better and better embedding models that are coming out in the near future. So it's something just to keep your eye on as we move forward in this very fast moving space.
And that's their latest embedding model, the one they recommend using as well.
Right.
There are some older ones, but this one is, if you go to OpenAI's website, in the documentation, this is the embedding model they recommend using.
Exactly.
And what that embedding model, yeah, sorry, I keep interrupting. I was going to say what that embedding model is going to do is take your query and take your data, and it's actually going to embed them and convert the text into vectors. So that's we didn't cover the vector database introduction today. But for those that are not familiar with this, it's just creating vectors which have the context of the text that's being submitted to it. Yeah.
Perfect. Thank you. All right. So we've got our embedding model picked out, and we need to set up our vector database. So we're going to be using KDB.AI. And like Neil said at the beginning, you can go ahead and sign up for an account. And once you are all signed up, you'll get access to your endpoint and your API key. So I've got that all here. I already put that in. And then we instantiate the session. So this just allows us to talk from like this notebook to KDB.AI. So you put in your API key and your endpoint there, so that connection's set up. And now we're going to define the schema for our table. So when we're creating this vector database, it's within a table in KDB.AI. So here we're defining a few different columns. We got an ID column and a text column. And then we have our embeddings column. So this is the one where you're actually doing that similarity search against. And it's a vector index. So you define a few different things. So you define the number of dimensions, as well as your search metric. So there's a few different search methodologies you can use. Like I mentioned, we're using Euclidean distance here, but you can also use cosine similarity or dot product. So all that information's in the KDB.AI documentation if you're interested in trying a different search metric. And then the type of index that we're using for our vector database. We're just using a flat index for now, but there's like 4 or 5 different options you can use there. But for this POC and notebook, this will work just fine, just using a flat index. So let's run this, make sure we got that good. We'll set up our schema. And then what we're going to do here is just check to make sure we don't already have a table named LangChain, because that's the table we want to create. And then we'll go ahead and actually create this table. So this is going to just take a second to run there. But once we've created the table, the next step is actually putting our chunks into the vector database. Okay, so this is how we do that. So we take our KDB.AI and we put a few different variables in here. Our session, which is just that connection between KDB.AI and the notebook. The table that we just created, like LangChain. Our chunks that we chunked up above. And then the embedding model that we just chose, which is the OpenAI ADA 002 model. So once we run this, we will have a vector database that contains all of our chunked up documentation in that vector format. So if we just take a look back at the architecture, at this point, our vector store is filled up with all of our chunked up and embedded data. So now we can do some similarity searches. And so let's just try it out here. So we'll create a query, what are the nation's strengths? And we'll run that. And then we will go ahead and do the similarity search. So this is running a Euclidean distance similarity search between this query and our vector database. And what we get out is a chunk in chunks of relevant information. So this is retrieval right here. We are retrieving relevant information. So in the grand reg pipeline, this is where you retrieve your information, and then you would send this relevant information to our large language model. So this completes that first retrieval step in reg. All right, so we have that, and now let's do it. Let's do retrieval augmented generation. And what we're going to do here is define those two large language models. So we're going to use our OpenAI Text DaVinci 003, which is GPT-3, and then we're going to use a Hugging Face LLM from Google called Flan T5XXL. And we're just going to use both of these just to see if there's any difference between the two. So let's go ahead and give it a try here. So we got them both defined here, LLM OpenAI, LLM Flan, and now we can create a chain for each model. So how this works is in LangChain, this sets up the process for you to actually hand a list of documents or relevant chunks into our large language model and pass them in as part of the prompt that would be prompting that large language model. So we set up that chain here. So we have two chains, both the OpenAI chain and the Hugging Face chain. And we got our query, or our related chunk here that we just got from above. This is just showing it one more time. And now let's do it. So this is where we actually run our RAG pipeline from start to finish. Is we got our query sim from above, which is the similar chunks, and we have the query, which we pass in as well. And we can run this, and we'll see what it says. The strength of the nation is the American people who have the potential to turn every crisis into an opportunity. So it's all based on that relevant information that it was passed, and it's a decent answer. But let's try the Hugging Face one and just see what happens. It says possibilities. So why is this? This is kind of interesting. So I did a little digging, and the reason this happens is that the Google Flan T5 is really it's a model that specializes in like short, specific answers. So when you're asking like a big, broad question, like what are the strengths of the nation, it's not really going to effectively be able to answer that with the same amount of accuracy as the OpenAI models like GPT-3 or ChatGPT models could. So in this case, if we were building an application, we would not want to use this, and we would probably lean closer to using one of the OpenAI options. All right. And then we're going to try this one more time with a different retrieval method called Retrieval QA. And this is like a wrapper sort of around what we just did. You include the retriever within the call when you're creating your LLM chain. And the difference here is we can actually specify the number of related chunks we're going to be sending to the large language model. So in this case, we're going to say, let's send 10 chunks to our large language model, 10 of the most related chunks to our large language model. So we have our chain type, which is just the thing that sends our or our related chunks to the LLM in the prompt. We are choosing to use GPT 3.5 Turbo, which is the underlying model of ChatGPT. And then for our retriever, we have, of course, set up our vector database within KDB.AI, and we're using that as our retriever. And we are looking to get K number of chunks back from KDB.AI. So we want to get the 10 related chunks.
I think temperature is something interesting to talk about too. So temperature is almost a creativity meter or hallucination meter. If you set that temperature to 100, it's going to be more creative, and but as a result, it'll hallucinate more. If you set that temperature to 0, it's going to be more precise in its answers, and it's not going to hallucinate.
Yeah,
well, not nearly as much. It's going to be it's going to attempt to give you very specific answers.
Yeah, that's a great point. So if we want those specific answers, or it's more of like an academic use case where we don't want things to be kind of made up and a little bit more flexible, then we would want to set a low temperature. So in this case, we're just using 0, but this is something you can experiment with. If you wanted to spice it up a little bit, you could increase the temperature and see what happens. So we'll run that. I think I ran this already. Make sure I got everything going here. All right. So now we can send it a query, which is what are the nation's strengths. So let's see what happens here. It takes a second to do this. I think the heavier the model, the longer it takes. So we'll give it a minute.
This is something where if you get an application, you might show it typing out the response as it's generating the response. But here in this Python notebook, it's just going to generate the response, and then it's going to generate the full response and then display it.
Yeah, exactly. So here we see, oh wow, we get a big list of all the nation's strengths that it pulled from all of the relevant documentation that it was provided, and it's a really good answer. So in this case, we see there is a pretty significant difference even between 3.0 GPT-3 and then 3.5. So this stuff's moving quick. And then we can try one more here, just with a different type of, or a different query there. and this will take another minute to go. But yeah, it's pretty interesting just to try some different models. You could try different temperatures, try just different number of chunks that you're sending in. So all things to
It's
experiment.
also interesting. I think it's also interesting because sometimes you may want naive rag. You may not. You may want it to only talk about the topics that are in your vector database.
Right.
You may want it to not reach out to not go out to the rest of the LM data and find other responses. You want it to be specific to your data. So I think this is interesting
True.
for that. But yeah.
Yeah, so here we just get a similar response. It didn't format it for some reason, but it's giving you a bunch of points about the things that the country needs to protect. If you read through this, it's pretty good. So pretty good response. But yeah, so this is the presentation, and this is the code that was walked through. And then just the last step, if you're done experimenting with this, you can go ahead and drop the table, just so we're not using unnecessary resources there when you're done. But yeah, thank you all for joining. And if there's any questions, I'm happy to answer.
Yeah, we had a question from Prabhu in the chat. He's actually asked another question, or he has just an observation. I think it's worth highlighting. It'd be interesting to come up with a measure that gives an idea of how much RAG has helped in producing the final response. I think if you look at LangChain's website, they do offer some paid services with observability. I was looking into that a little bit last night, but definitely a good observation. Observability is another key area that we should probably produce some sessions on, Ryan. We'll
Yeah,
work with it in the future.
that's a great point.
But if you guys enjoyed this session, you all enjoyed the session, then follow Ryan on LinkedIn. You can follow either of us on LinkedIn or both of us on LinkedIn. And just to let you know, next week we are going to do sentiment analysis with vector databases. I will be out next week, but our head of evangelism, Dan Baker, will be leading the show with Laura Kerr doing the sample. So we're really doing the sample exercise. So we're really excited about that. Sentiment analysis is like predicting positive, negative, neutral emotions and sentiment in different texts, and how that can be done with vector databases. And just to let you know what our upcoming sessions are, so we're doing sentiment analysis on November 1st. Approaches to RAG, Ryan will be back with us to do approaches to RAG on November 8th. And then on November 15th, Michaela is going to join us to do improving RAG performance. And on November 29th, we'll do some chunking methods. We will take the week of Thanksgiving off, just with people being out for the holiday in the US. But feel free to join any of these sessions. Again, Wednesday, 11:30 a.m. Eastern, 4:30 p.m. UK time. We're keeping these live streams going, and if there's any topics that you all want to see, feel free to message us on LinkedIn, and we can add those to our queue. But with that, thank you all for joining today. Hope you have a great week ahead, and we will see you next time. And thanks, Ryan, for your great presentation.
Thank you. Thanks for joining.